Welcome, my dear students, to another week of chemistry with Mr. Miguel. This week, we will be covering the evidence for the particulate theory of matter. The objectives for this week are the following. However, let us start with a small review of the particulate theory of matter. What is it? What do we mean by the particulate theory of matter? First one, all matter is composed of particles. That is why it's called the particulate theory of matter. Number two, there are spaces between particles. Number three, there is attraction between particles. And number four, particles are in constant random motion. Let's look at objective number two. What is the evidence that speaks for the particulate theory of matter? We have three, but we start with Brownian motion. And Brownian motion is a type of movement in which particles move randomly. And it was observed by Sir Robert Brown, which is depicted here on the image. And Sir Robert Brown, he was a botanist, and when he was observing under the microscope pollen grains, he observed that the pollens were moving. So what he did, he closed the container and he observed it once more. Even though there was no movement of the table, no movement of the microscope, and the container was sealed, there was no air entering the container, particles, specifically pollens, continued to move. And he said, why are they moving? Well, it was later known that it was the water molecules that were moving, and when they move, they caused the particles, the pollen particles, to move, as seen on the video here.
You're in a darkened room, the air is still, and the bright lights are streaming through the window. What do you notice about the dust particles? The black circles as they pass through the beam of light. Pause the video and think about this. Press play once you've made up your mind. The answer is that the dust particles are moving randomly. Did you see it? The dust particles are not always moving downwards, but are moving in all directions. The dust particles are very small and are supported by a fluid. In this case, that fluid is a gas. You are unable to see the gas particles directly because they are too small, but you can see the larger dust particles. The reason that the dust particles move randomly are because of the gas. We know that the gas is there because every time we move our hand through the air, we feel them against our hand. Try it now. Continue when ready. The particles in the air move in random directions quickly. This means they will have many collisions or will bump into the dust particles many times. Each collision between air particles, very small coloured circles, show how the dust particle, the black circle, moves off in a new random direction. It's a bit like a game of snooker, where there are millions of marbles which collide with larger, observable particles like a ping-pong ball. This effect was first observed by scientist Robert Brown. He was looking at pollen grains suspended in water under the microscope, and he wondered why they jiggled around. He thought that the pollen was alive. It was later that scientists realized the importance of his discovery. Now, here's a challenge for you. Thinking about what we know about dust particles, can you explain why the pollen grains appear to be jiggling randomly? Pause the video and continue when ready. In summary, the fluid is no longer a gas, but is a liquid, water. The pollen grain is colliding with many water molecules. Each water molecule is too small to see, but we can see the combined effect of their collisions on the pollen grain as it moves randomly. This effect is known as, you guessed it, Brownian motion.
Now let us look at objective number 4. Objective number 4 speaks about diffusion. And diffusion is practically, in simple words, the process in which particles move and spread and distribute themselves. So when particles distribute themselves or spread themselves, that is what we call diffusion. That is the same reason why we're able to smell food from far away, since food particles are ejected from the food material and end up in our nostrils, which we identify as food. So if we were to look molecularly at how diffusion works, it would work like this. So you have a high concentration of particles on this side. That means that they are bunched up together. High concentration means that there is a large abundance of particles there. But particles don't like being together. Why? Because they're in constant random motion, so they're knocking against each other. And when they knock against each other, they start moving. And they move towards areas where they will have more space for movement. And those areas we call areas of low concentration. Therefore, when we define diffusion, we say that diffusion is the movement of particles from an area of high concentration to an area of low concentration. How does this prove the particulate theory of matter? First of all, it allows us to see that matter is made out of particles. Second, it allows us to see that particles are in constant random motion. Third, there are spaces between particles. So this theory, the theory of diffusion, allows us to support the particulate theory of matter. Let's look at. So this video will show you exactly how diffusion works.
Molecules dissolved in a solution are in constant random motion due to their kinetic energy. One result of this motion is that dissolved molecules become evenly distributed throughout the solution. This tendency of molecules to spread out is an example of diffusion. But how do these molecules come to be evenly distributed? Let's start with a beaker of plain water. What will happen if we now add a lump of sugar to the water? A lump of sugar is composed of many individual sugar molecules, and even as a solid lump, the individual sugar molecules are in motion. When the lump is dropped into the water, it begins to dissolve. Individual sugar molecules move randomly and constantly from the area where they are common to the area where they are scarce. This type of motion, when molecules move from areas of their higher concentration to areas of their lower concentration, is called diffusion. Diffusion continues until all the sugar molecules become evenly dispersed throughout the beaker. The rate of diffusion is affected by temperature, size of molecules, and the steepness of the concentration gradient. Although not specifically shown in this animation, this is one of the processes whereby materials are exchanged between a cell and its environment.
We are able to see also diffusion in this scenario. If you're able to see the cups, they contain water. And if you add a little bit of Kool-Aid or food coloring into the cup, the Kool-Aid starts to spread and the cup eventually becomes colorized with whatever dye you put on it. I am saying this: if you add a drop of dye onto the cup, allow it to sit there, eventually the color of the water will change even if you did not stir. Okay, so that's what I'm saying, and that is the process of diffusion in simple words. Can you think of diffusion at your home? Maybe Kool-Aid, coffee, sugar. Think about it. In this experiment, diffusion was demonstrated. So they put ammonia, a cotton with ammonia on one side, and ammonia, when the temperatures get high, they become gaseous. They become a gas. So the ammonia is going to travel in gaseous form through this tube. And they will put hydrogen chloride, also known as hydrochloric acid, in the other side. When the temperature increases, the particles from the hydrochloric acid will move through the tube towards the middle. When they meet in the middle, they will form a salt because they will chemically combine with each other. When they chemically combine with each other, it shows that particles moved from the cotton. So there was a cotton. From the cotton, they move towards the center and they form a little salt ring. So it will look like salt, like literally table salt. and that would prove diffusion. This is one of the common experiments that is demonstrated in chemistry. Now we will discuss how osmosis can prove the particulate theory of matter. As you can see in this video, which will play now, osmosis is a type of diffusion. So let me play the video for you.
Diffusion is the net movement of molecules down a concentration gradient. This process allows small molecules, such as oxygen and carbon dioxide, to cross the plasma membrane. Most polar molecules, such as sugars and proteins, cannot freely cross this lipid membrane. Although water molecules are polar, they are small enough to pass through the membrane freely. This special case of diffusion that involves the movement of water molecules across a membrane is called osmosis. If a molecule, such as urea, is added to one side of a membrane, it will not be able to diffuse across the membrane because it is both large and polar. Because of its polar nature, it will interact with other polar molecules such as the water. This interaction reduces the number of free water molecules on the right-hand side. With fewer free water molecules on the right-hand side, there is now a net movement of water molecules down their concentration gradient to the side with the urea molecules. Because more water molecules are moving into this area than are leaving, the water level on the right side will rise. If the osmotic concentrations of two solutions are equal, the solutions are isotonic. However, when the solutions have unequal osmotic concentrations, the solution with the higher concentration of solutes is hypertonic, and the solution with the lower concentration of solutes is hypotonic.
So from the video, we could learn that osmosis is defined as the movement of water molecules. I want to emphasize something. It is very important that you remember that osmosis is the movement of water molecules or solvent molecules, since water is a universal solvent, but the movement of water molecules. Since you're in high school, I want you to underline this word, water molecules. In diffusion, it's just the movement of particles in general, but in osmosis, it's the movement of water molecules through a differentially permeable membrane, which means like a selectively permeable membrane. So let me give you an example. You see, when you want to mix your sand with cement, but you need to take out the gravel, and you grab un colador. See? Okay, that colador is a differentially permeable membrane. This means that it provides some way of filtering the substance. So if you think like that, a differentially permeable membrane is like a little cloth with little holes that allow water particles to move through it. Okay, but particles don't only move, water does not only move randomly. It moves from an area where there's a lot of water to an area where there's less water. And this is more or less what osmosis is. And osmosis proves the particulate theory of matter because it shows that particles are in constant random motion and that matter is made out of particles. One more thing I want to clarify in this video. I want you to look at the diagram below you. Each of the blue dots represents a water molecule. So in this case, how many water molecules do we have? So we have 13 water molecules. And how many salt? Let's say that the solute is the salt. How many do we have? We have 5. Let us say that there is 90% water here. What would be the concentration of salt? If we were to look at the concentration of salt, it would be 10% salt. So in this solution, we have 10% salt and 90% water. Now let me draw another circle. That's the salt, this is the water. And let us say that in this case we have 97% water and we have 3% salt. In which direction do you expect the water to move? Remember that osmosis is the movement of water through a selectively permeable membrane. Let's say that there is a little membrane here, from an area where there's a lot of water to an area where there's less water. So in which direction should this move? So I'll give you 1 second to think. Here we have 90% water and here we have 97% water. Where do we have more water in terms of percentage? Here. Therefore, water will start moving from here, from this circle to the next circle. Since we've seen the video, now let us look at this example. How would we work this out? So this one tells you how much salt is found within the cell, in the first example, and outside of the cell. In this one, how much water would be found inside of the cell? Since we know that inside of the cell we have 5% salt, how much percent water will we have inside of the cell? We will have 95% water. Now, if we have 10% salt outside of the cell, how much percent water will we have outside of the cell? 90%. Therefore, the movement will be in this direction. So, from inside, so the movement will be from let's look at this example. In this example, you're able to see a permeable membrane, which is this bag right here. That means that this little bag allows water to enter and exit the cell, but it does not allow salt molecules to move from it, between it. And it's known as a whisking tube, and it's used in dialysis. It can be used in dialysis. Therefore, in what direction can you expect the water to move in this case? So we have 100% water here, and in the whisking tube we have, let's say we have 70% water. Since we are seeing that it has sucrose solution, that means it has sugar dissolved in it. So let's assume that it has 70%. From where to where will water move? It will move from the outside towards the inside, causing this structure, the whisking tube, would expand and become bigger. What would happen to the level of the water? It would decrease. So what are the practical uses of osmosis at home? Well, for one, it's used to control pests. Once you see slugs at home, you add salt on top of the slug and the slug becomes watery. Is it really becoming watery? No. It means that this is the slug. This is how the slug would look like. And you add salt on top of it. Remember that water will move from where there's a lot of water to where there's less water. So outside of the slug there is less water. Therefore, the water from inside the slug will move out. And when it moves out, it will cause this slug to shrivel up and desiccate. So this slug would die. So we can use the process of osmosis in order to control garden pests. We can also use it in preserving food because bacteria, once it has salt outside, the water will exit the bacteria, causing it to die. Therefore, it prevents food from rotting. So that's practically osmosis. Now think of yourself, how can you use osmosis at home? And that is the end of the presentation for this week. Have a blessed rest of the day.